So what's the answer? Talk to your neighbor for a second.
Oh, wait.
All right, so what do you think? Come on, guys. Hold up some fingers. Let's see fingers. All right, 4. Yes. So why don't you conclude that the tape is positively charged if it's attracted to a negative object? What dipoles?
It could be an induced dipole.
Oh, induced dipoles. In what? In the tape. Okay. So if we have something that's negatively charged, the tape molecules in the tape could polarize, and now the tape, the positive charges are attracted to the negative charges are repelled, but they're a little farther away, so the net force is in fact an attraction. So attraction isn't a particularly good test for the charge of an object, whereas repulsion, the only way something can repel charge, right? And we're building up some conventions for drawing diagrams of polarization. And so far, what we have is that when we draw an object, this represents the surface of the object, and anything in here is, and anything drawn right here is on the surface. Okay? So how would could an object be both charged and polarized? So this is a neutral object in our diagram that got polarized. Could an object be charged and polarized? Okay, we have one no. So what happens if we have a plastic ball, a solid plastic ball like a billiard ball or something, and we rub this side with our wool sweater. So we get some negative charge on the surface of the plastic. So now we agree this is a charged object, right? Are these charges going to spread out all over the surface? Not on a plastic, not on an insulator, right? Insulators don't have a way for charges to move either on or through them. So, but what happens to molecules inside here? Okay, so here's some negative charge. What's going to happen to a molecule right here? It is going to polarize, isn't it? So this object is now both charged and polarized. Or we could polarize it even more by putting a big negative charge out there. So these are two different words. Charged means net charge, non-zero. and polarized means a little bit of charge separation and atoms or molecules inside the insulator, okay? So this is a polarized atom or molecule. As some of you said, it's an induced dipole. And the electron cloud shifts just a little bit. We made an estimate in one situation where we found in an atom the electron cloud might have shifted as much as a nuclear diameter to make that atom into a dipole, so it doesn't have to shift a lot. Okay, let's see. Okay, well, we just did that. All right, we're done. However, so yes, last time we talked about objects that don't have mobile charges, which we call insulators. But that's not every object in the world. Things are made of metal, or salt solutions or whatnot do have mobile charges. And so today what we're going to talk about is conductors, things that have mobile charges. One of the most familiar kinds of a conductor would be a salt solution, probably. So we have a beaker of water in which we've dissolved some sodium chloride. So we've got some sodium ions and some chloride ions. Lots of them. And they're free to move. So if there was something out here that was charged and created an electric field inside this solution, then these ions could move depending on the direction of the electric field. If we have an electric field, we'll call this the applied electric field. Which direction will the sodium ions move? In the direction of the field, right? So, and which direction will the chloride ions? The other way. Now we can be, so, and long distance motion is possible. So instead of a fraction of a nuclear diameter, this sodium ion could potentially move all the way over here. Centimeters or meters if we gave it enough time. So there's a big distinction between mobile charges and charges that can just shift a little bit. Now we can be a little bit quantitative about this. We can talk about the drift speed of a charge that's moving under the influence of an electric field. So the average drift speed, and that is a bar for average, not an arrow for vector. We're talking about a speed here. We're talking about magnitudes. Is directly proportional to the magnitude of the field that's the net field at the location of the charge. And the proportionality constant is, we use the symbol lowercase Greek mu and it stands for mobility. And since this has units of meters per second and this has units of newtons per coulomb, mobility must have the units of meters per second per newton per coulomb. Sometimes that's a U also. So could be a U. Now this is sort of a little peculiar, maybe, in the sense that we know from the momentum principle that if we apply a force, what the force does is change the momentum, and so a constant force keeps changing momentum, a constant net force. And since the force must be QE, it seems like really this should be giving us a rate of change of momentum and not just a speed. So why isn't it? Is there anything besides the electric field exerting a force on this ion here? Here's the electric field exerting a force. What's the ion have to move through? Stuff, water, solvent. Okay, so basically it's a dissipative medium. There's something very much like friction. It's drag, right? Okay, and so in fact, because there's this mechanism of transfer of momentum to the solvent and whatnot, it turns out that in fact the speed really is directly proportional to the applied electric field, and the proportionality constant is the mobility. Yes?
So is it kind of like, because of what's hit in, it's kind of like a terminal velocity?
It's kind of like, yeah, you could think of it as a terminal speed, yeah. And now this is an average speed, because probably what's happening is it speeds up a little and then it collides with energy and slows down and speeds up a little, and so you can kind of think of it as basically like wind. So even in a situation where there is no wind, air molecules are moving around in all directions randomly at rather high speeds, actually. So hundreds of meters per second anyway. But what's a wind then? Well, the wind comes along and there's something that makes a large but much slower collective motion in one direction. And all these air molecules are still zipping around in other directions, but added on to their velocities is this drift velocity in the direction of the wind, and that's basically what's happening in these conductors. So we're getting a constant flow of charge. So if we had an electric field of 200 newtons per coulomb, and the mobility for a chloride ion was about 8 times 10 to the negative 8th, I think it is. I think I looked it up. Meters per second per newton per coulomb. So what would the average drift speed be? Well, 8 times 2 is 16, right? So we have 1600 times 10 to the negative 8th, or we have 1.6 times 10 to the negative fifth meters per second, something like that. So not real fast. But there's a lot of ions in this solution. So getting the number of ions reaching this wall of the beaker could be fairly large, even though they're drifting sort of majestically through the solution at low speed. So let's write so let's think about what's going to happen when we apply an electric field to a conductor, something that has mobile charges. So here's our beaker of salt water with plus and minus charges. We put a positive charge here. It creates an electric field there. So let's take this. So what's going to happen? We get this flow of charges, which is a current. That's what an electric current is a flow of charges. But is it going to go on forever? Let's think about what's going to happen sort of in nanosecond steps. So in the first nanosecond, these sodium ions feel a force that way, and the chloride ions run that way. The chloride ions feel a force that way. And so this whole sea of ions, all the negative ions move that way a little, all the positive ions move that way a little. The ones that were close to the edge of the beaker can't go any further. So we start to pile up a little bit of negative charge here and a little bit of positive charge here. But that's interesting, because now we have a new source of charges. So in here it's still neutral. We have the same number of pluses and minuses, but over here we've got this excess of negative charge. And over here we've got this excess of positive charge. Well, these charges make fields, don't they? We have a new source of field. So inside here, now what we've got is we've got this field hasn't changed, but now we have an electric field due to the negative charges over here. We have an electric field due to the positive charges over here. So the net field inside the beaker is actually now smaller than the applied field. Now what we've got is a so E net just got smaller. But it's not zero yet. So it's smaller. So the drift speed of these ions goes down, right? But they're still drifting along. And so we're going to get, what's going to happen over here? Some more negative charges. And over here we're going to get some more positive charges. And now, in the next nanosecond, this is still neutral, but I'm going to erase that circle just because this is getting super cluttered. But now, the electric field due to the negative charges is a little bigger, and the electric field due to the positive charges is a little bigger. And our net field, which is the sum of all these fields, got smaller still, right? Now it's only about so we're going to keep going. What's going to happen? What's going to happen? Is it going to keep going and going and going, or is it? It's going to run out, isn't it? It's going to, when we get to the point where we have enough negative charge and enough positive charge that these new fields add up to a zero net field in here, then the drift speed goes to zero, doesn't it? Because even if they had a little momentum, they collide with the solvent and they stop moving. And so eventually we get to this point where this conductor polarizes. So now we have a polarized conductor, and it polarizes until the net field inside goes to zero. And interestingly, that's the net field everywhere that has to be zero. So it's not only zero here, but it has to be zero there, and zero there, and zero there, and zero there. So we might get a kind of complicated distribution of charges around the around the inside of the beaker. Now, even though charges are drawn, they've drawn inside the beaker, they're really at the surface of the water. So they're really basically on the surface of the conductor itself. Okay? So the excess charges all go to the surface, and that's plausible, right? Because they're, and we can't prove it yet, but we will. And so charges flow until we get to a point where the net field everywhere inside that conductor goes to zero, and then it stops. And now we've reached what's called equilibrium. So equilibrium and now this is a conductor. No net charge flow because E net is zero inside, so the average drift speed is zero. So this all sort of hangs together. Now this is actually almost a mathematical syllogism here. It's what we can do what's called a proof by contradiction. Do you know what a proof by contradiction is? Yeah, so you assume the opposite of what you're trying to prove. You show that it leads to some contradiction, and then you conclude that your assumption was wrong. So if we assume that inside a conductor at equilibrium, E net is not zero, say, well, it doesn't have to be zero at equilibrium. But if it's not zero, then the drift speed of the charges won't be zero. There'll be net charge flow, And that's not our definition of equilibrium, so we just reached a contradiction. So therefore, at equilibrium in a conductor, the flow is charges aren't moving around, they're bouncing around, but there's not a net flow in any given direction. Okay, so that was sort of Claire with a beaker of salt water. Do you have questions or comments about that? Yes?
So all the charges go to the ends and the
Okay, so that's an important question. Do all the charges go to the outside? It's certainly neutral in here, but do all the charges go to the outside? And that's a quantitative question, and the answer is no, actually not very. It doesn't take very many, because these excess charges here and here make a fairly large field. So it doesn't take all of the charges in here, so there are plenty of charges in here. There's still sodium ions and chloride ions, and just a few of them have piled up here and a few there. And how many? Well, it depends on how big a field you applied. But even if you apply a very large field, there's still going to be a lot of ions left. We're talking about 10 to the 23rd things here. It's positive and net negative, that's right. Now, there's a diagrammatic convention here. So here's our conductor. I'm actually going to draw these excess charges just outside the boundary. This is the surface of the water, basically, that I'm talking about. So at surface. And then inside, although plus, minus, as long as I had equal numbers, it would be neutral, right? That's just visually annoying, because then you have to count to see if somebody really drew exactly the same number, if they meant there was actually some charge in here. So our convention is that when something is neutral, don't draw charges. So that could be there is no charge there. It could be there are equal numbers of positive and negative. It's net charge 0. Okay. And that makes our drawing and interpreting diagrams a whole lot simpler. Because it turns out diagrams are a really good way to communicate about a lot of these processes. And we don't want to spend all day drawing them. Okay, so we know where the ions are and the mobile charges are in a salt solution. That's easy. What about a metal? So we have this model of a metal, the whole ball spring thing. And let's see if we have a picture of the ball spring model in this. I don't. Well, remember that we modeled a metal as a lattice of massive objects, which were the nucleus and the inner electrons connected by spring-like covalent bonds. But where are the mobile charges? We know metals are conductors. We saw that aluminum foil, if we put it in a circuit, would let a light bulb light. You all have a strong belief that metals are conductors, and they're very good conductors, right? But where are the mobile charges? Well, this thing is neutral, right? So what happens in a metal is very interesting, and we have to refine our model of metals a little bit here. In a metal, it turns out that every gives up one electron. To form what we call the mobile electron C in a metal. Now, so what we end up with really is that each of these massive objects has a net positive charge, and then this whole thing is bathed in a sea of electrons, which came from every atom giving up one electron. And that's an interesting thing about metals, and it explains a lot of the interesting properties of metals, like why they're shiny and why they're conductors. So now we have a situation where we've got what we're going to call a positive atomic core. So the core of the atom minus the outer electron. And then a sea of mobile electrons. So that the interior of the metal really is neutral, but now we have this sea of electrons that can shift back and forth or can flow in some direction, which makes it an extremely good conductor. And so a sort of schematic model of what's going on in a metal might look something like this, where we have all these atomic cores that are sitting still because they're still bonded together with these covalent bonds. Okay, so they're vibrating a little bit, but they're not going anywhere. But we have this whole sea of mobile electrons that can drift in some direction if a field is applied. Now let's see, the electrons are moving that way, so what do we think the direction of the applied electric field that's making them move is? Right, must be that way. And if we reverse the direction of the electric field, the electrons would go the other way. And it's still the case that the drift speed is given by the mobility multiplied, the average drift speed of these electrons is given by the mobility of the electrons, which is a function of the particular material, times the net electric field inside the metal. And because the mobilities of electrons in metals tend to be fairly high, we don't need very big electric fields to make currents flow, but we still need some. So why do we need some? Well, there's still this effective drag or friction or whatever you want to call it going on inside the metal. And it results from a model. It's a simple model, but it's reasonably effective due to a physicist named Drude, so it's called the Drude model, is that an electron in the metal here feels an electric field, and so there's a net force on it, so its momentum increases until it crashes into one of the positive atomic cores in the lattice. It's a chalk. And then what happens? Well, some of that energy goes into the lattice, so the lattice starts vibrating a little more, it gets hot. So the temperature increases, as we saw last semester, because temperature is correlated with vibrational energy. And then it came to a stop and it transferred all of its energy to the lattice, but that field is still there, so it speeds up again until it crashes into the next. So there's this kind of accelerate and stop motion. And if we graphed something like the speed of an electron versus time in the presence of an electric field, we might get something like this, where there's an electric field, so it speeds up, speeds up, speeds up, crashes into the lattice and stops, but there's still a field, but this time it doesn't get to go as far, so before it collides, because it's probabilistic. And then it speeds up again, and there's some... And so it's rarely actually traveling at this drift speed. So the drift speed is a time average. But its average speed is probably something like that. Right? So it's from this accelerated stop motion. So we can actually get a handle on what mobility is related to here. So we say, thinking in one dimension, px final is px initial plus f net x delta t. We're starting from rest. And what's this? Well, this is the charge on the electron times E net delta t. So V final in one of these time intervals is going to be, we're dividing through here by m, so we get E net delta t over the mass of the electron. And we can rearrange this, so we say Vx final is E delta t over m times E net, and it sure looks like that is related to the mobility of the electron. So it's the charge on the mobile charge, the mass of the mobile charge, and then the average collision time, the average time that it gets to go between collisions. And so it would be, we'd have to average this delta t and that delta t, and so this would be an average if this is average delta t between the collisions. All right. Questions? Let's review a little bit. Okay, so we have a region of space. There's an electric field in the plus y direction due to, this is the applied field, due to some external charges. We don't know what they are, but we know they're making a field. And we put a block of copper that's originally neutral in this region. Which of these diagrams, using our conventions, best describes the charge distribution on the block of copper? What do you think? Yeah, 1. Because, and how did that happen? I mean, it started out neutral. How do we get this charge separation? What moved? What are the charged particles that move? Protons? Our mobile electron C just all shifted a little bit, doesn't it? So if we draw this, what we mean are, what are these positive charges? Well, these are positive cores that are a little bit exposed, and these are, so the whole sea of mobile electrons just shifted down very far. Tiny fraction of an atomic diameter, because there's so many electrons there. Okay. Now suppose we had an iron block that started out negatively charged, and we'll talk about how that we might be able to do that. And we applied an electric field in the -y direction. So how would we draw the result? You might want to talk to each other about this one. Okay, what do you think? Okay, I'm seeing 3s and 2s. Okay, so now the key here is actually counting charges. Because if the block is negatively charged, then that means it has a non-zero net charge, right? And that means, what about the number of positive and negative charges in the block? More negative. And so, even though this is the right direction, if we count here, it looks like there's the same number of positive and negative charges, and that doesn't correspond to the situation that we described, which is the block started out with some excess electrons, right? So therefore, in fact, this is an appropriate diagram for that situation. Now, how do we get an excess charge on a metal block? Well, charging by contact still works. So you saw charging by contact when you charged a piece of invisible tape by putting it in contact with something else and then separating them. It is possible to charge metals by contact. It's a little harder. But you've probably seen a Van de Graaff generator, the thing that has a big sphere, and if you stand on an insulated thing and put your hand on it, your hair all stands up and it's cool, right? Okay, so we get this big charged sphere, and the reason I'm not showing you one is that it's very hard to make them work in humid weather. You kind of have to dry them out for a day. Oh, we do have something I could have brought, but that works by, there are some little metal brushes brushing against a moving belt, and just that contact is enough to move some charge from one object to another. Okay. Let's see, which number is this? 7A. There we go. So here's another aspect of metals and charging. So we have two identical metal blocks. We start out with one of them is neutral, and the other has a deficiency of electrons here. So its charge is plus 6 nanocoulombs. And then, yeah, what?
When it says the blocks touch, are they instantaneously touching and being pulled away, or do they touch for a while and then be pulled away?
So the blocks touch, and let's say that they touch for, the question is it for a really short time or a long time? The answer is it might not matter, but let's make it a really long time, because these processes are pretty quick. But let's make it 10 minutes, okay? So now it's fractions of a nanosecond that really matter here, but so they touch, and you're handling them with rubber gloves, so insulator, and then you separate them. So what is the final charge on block B? So what do you think? I'm seeing 2s, and I'm seeing I'm not playing today. Come on, guys, take a risk. All right, we'll accept 2. Yeah, 2 is correct. The charge spreads out equally across these identical blocks. Why? Well, equilibrium is sort of actually a fairly profound way of saying it, but the mechanism is the positive charges don't particularly want to, excess positive charges don't particularly want to be close together. They're repelling each other, right? So now but is it positive charges that are moving from block A to block B? What moved? And which way did they move? From B to A, that's right. We have mobile electron C, and some of those mobile electrons move from B to A, decreasing the charge on A and making B partly positive. Okay. So there's actually an interesting aspect of charging by contact. We talk about grounding something to neutralize it. So the idea of grounding a conductor is that if we had some object that had, let's say, excess negative charge, here's the Earth. Now the Earth is wet and has lots of ions in it. So if we connect this by a metal rod to the Earth, what's going to happen to these excess electrons? They're gonna spread out to get as far away from each other as possible, presumably. So they're happy to flow down this metal rod into the Earth, and then they have a very large surface to spread out over. They have such a large surface to spread out over that, in fact, there might be essentially nothing left on that ball. So it's a way of allowing excess charge to spread out over a huge conducting surface area. What would have happened if this sphere was positive instead of negative? Electrons move the other way, right? So the electrons are going to come here. We're going to end up with a tiny positive charge on the Earth, and enough electrons will come up that essentially we're neutralizing it. Now, sometimes we talk about grounding or discharging something if we have a charged object just by touching it ourselves. So what's happening if we have I had a charged piece of aluminum foil. And let's say I'm wearing rubber-soled shoes, so so this is an insulator. So what happens here? Kind of the same thing, right? I mean, but how do charges spread out across U? So what's with U that you've got? Where are the mobile charges in U that would make U a conductor? Yeah.
Aren't we mostly water?
We are mostly water, so they certainly charge inside. What's on your skin, though?
Oil ions?
And salt. Salt and water. There is oil, but oil. The surface of your skin is a conductor. Not a great one, but a reasonably good one. Plus, we're super polarizable, aren't we? So it's kind of complicated. So we're certainly going to get this bag of salt solution is going to polarize. So we'd surely have positive ions here and negative ions in our toes. But there's also sodium ions and chloride ions on our skin. And so negative electrons can flow onto our skin, probably reacting with a sodium ion. I don't think we're getting a lot of sodium on our skin because we'd probably get sodium hydroxide right away, but not very much, but a little bit, right? So there's some complicated chemistry going on, but the fact is that this negative charge can actually spread out all over us, and we're reasonably good at grounding things. We saw in lab that if you charged a tape by pulling it off another tape, like that, yeah, charged. So how could I make it neutral? Now this is an insulator, right? So there's no mobile charges. In the insulator, we tried it in a circuit. It didn't. Nothing happened. Can I neutralize it?
Yeah.
How?
Just touch it. Yeah.
Just touch it. Okay. So I'm going to run my hand along the non-sticky side. Let's see what that did. Yep, that neutralized it. So what happened, though? I mean, did electrons flow out of my hand? What happened? So it's the salt water thing again, isn't it? So in touching that, the ions on my skin. So if the tape is positive, I'm probably depositing a layer of chloride ions here. If it's negative, I'm probably depositing a layer of sodium ions there. And the result is that I probably made a really, really, really thin dipole, because surely the charge is on the sticky side, since that's the side we pulled up. And I touched the slippery side, so I deposited ions there. But the distance, the separation of those charges is so small that the tape acts as if it's actually neutral. So some fairly interesting phenomena going on here. Now there's another way to transfer charge with a conductor. And so let me talk you through what's happening here. So we have two aluminum blocks that are initially neutral, and they're just sitting there. So this is time one. The blocks are neutral. They're touching each other. Everything's boring. Then we bring a positively charged object, like a positively charged invisible tape, over here. We don't touch the blocks. We just leave it here. Now think about what's happening here. We're not touching. Leave it here. Then what we do, we leave this positive charge here, but we use insulating rubber gloves to move the blocks apart. So we take block B and we just move it over. And now we take the positive charge away. So what's the situation now? What's the charge of block A after we've done that? So think about it for a minute. You might need to draw a diagram. Talk to your neighbor. So what do you think? So I'm seeing 2. So you think block A is negative. We never touched it. Okay, so talk me through what happens here. Let's fill out the diagrams. So here's A and B at time 1. Not much happening. Now we've got a positive charge. So how do I think about this situation? Okay, so induced dipole is an okay thing to say if you're talking about the whole thing, right? Mostly we talk about induced dipoles. We're talking about polarizing molecules, but it's appropriate to say it polarizes the blocks. Okay, that's probably a cleaner statement. I know what you mean, and so how would I draw the situation at this point?
More negatives than A.
So more negatives in A, more positives in B. Where do I draw them? Am I going to draw this? What's happening here is that this is a conductor. So these negative charges are... So they're on the surface, aren't they? So I'm going to draw them just outside the envelope saying it's on the surface. And so therefore I should draw positives because the whole thing's neutral. And I better draw the same number. Okay. So schematically we've indicated that the mobile electron C is shifted this way, exposing some of these positive atomic cores over here and some excess electron density over here, right? So now at time equals 3, I still have this positive thing here, but I separate the blocks. How would I draw the state of this system?
The negative charges on A would still be, but positive would be more free throw.
Okay, so we've got this block as negative and that block is positive, right? So Caden's saying, well, because we've still got this positive charge here that's exerting a big effect, probably we've got negative charge here and positive charge here ish. And now if we take this positive charge away, now what do I draw? So are they going to be uniformly distributed?
No,
Why not?
they're not touching.
Because they're not what?
They're not touching.
They're not touching anything. So what would I do? Would I do... Is that what you want? No. Okay, why not?
You switch the charges.
Oh, because I switched the charges. Okay, so... Well, okay, so let's draw it the other way. Minus, 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 plus, plus. Is that what you want?
No.
Still no. Because... Are they interacting with each other? Yes, okay. So in fact, most likely, it's going to be something more like... And maybe something like indicates somehow that they're polarizing each other, right? Yes.
If you did separate them far enough, would it uniformly distribute like that?
If you separated them far enough, would it uniformly distribute? What do you guys think?
There's only the force, right? There's only the small because everything has like this force on it.
So electric field does approach zero as we get farther and farther away. So the interaction must get smaller and smaller, presumably. So if we actually have E equals 5, if we have block A here and block B over here, we could assert that the interaction is close to negligible, right? And therefore we could
How does that work though? Because we just said that, electrons when they move need an applied field, and there's no real applied field there. How do they?
Okay, so this is a good question. So how would it go from this situation to that when there's no applied field? So let's look at let's say that instantaneously we have, let's say we had a distribution of charge like this on a metal block. Okay? And there's nothing in the surroundings making a field. Oh, so let's take as our system this electron. Is there anything near this electron that makes a field at the the other electrons, right? Okay, so this electron is, or actually it might even be easier to consider let's consider the top electron. That's going to be slightly simpler. This one has a field due to this electron, which is pointing down, and a field due to that electron, which is a little smaller but pointing down. So there's actually going to be a force on that electron that's going to make it want to move away. This bottom electron, of course, is going to want to move away from these other electrons. So they still interact with each other. I mean, so the net field is not just the applied field, but it's the field due to any charges on it. So therefore, the electrons will end up trying to spread out as far away from each other as possible. Now it ends up, interestingly, that complicated. So here is, so what's this? So this is the result of a computer program that actually calculated the distribution of charge on the surface of a metal block which is polarized by an external charge. And negative is blue, positive is red, so the external point charge is positive. The so white is neutral. And the calculation is a little It can't be done in real time, so that was done offline. But what's being done here, what this program has, is the resulting surface charge distribution, and what we can look at is fields in real time. So first, let's just look at the charge distribution. So we see that, not terribly surprising, the end of this metal block nearest the positive charge has a lot of negative charge on it. And so the electron C shifted that way. Interestingly, we're seeing we kind of have a dynamic range issue here. You can't make things bluer than, so the amount of blue shows kind of proportional to the amount of charge. But you can see that it's actually building up a lot on sharp edges. And in fact, the charge actually kind of builds up on the corners a lot, interestingly. And then you can see that it's not actually symmetric, that the positive charge starts, it's not halfway positive charge. Here the shading's enough, you can see that there's a concentration of darker charge on the corner than there is in the middle of this face, so you can see the positive charge building up here. So let's look at the electric fields in this situation. So the magenta arrow is the field due to this external point charge. This is the applied field, and it's big, okay? So the applied field falls off like 1 over distance squared. And it's not 0 inside the metal. It's still there, okay? But if this thing's at equilibrium, the net field inside this metal block, it needs to be 0. And so what are the other charges that are going to contribute to that field to make it 0? All that charge on the surface, right? Yeah. And so if we look at the field due to the surface charges, which is shown in green here, we see that out here, of course, that there's a field toward the negative charges. Inside, the field is toward the green field, the field due to these polarization charges, the surface charges. Look how uniform it is. That's really interesting. And then out here, it's okay. So in here, notice that at any location in here, no matter where I drag this, these fields tend to be equal and opposite. So that's kind of a complicated distribution of surface charge to make that happen. And so if we show the net field, which will be shown in orange, out here the net field is big. Out here the net field is due to both the external charge and the surface charges. In here, the net field isn't showing up because it's 0. So in fact, interestingly, this rather complicated distribution of surface charge, which is not by any means uniform, is enough to actually make the net field 0. Now what we're doing here, we're measuring the field inside, but we're drawing it on the surface so we can see it. Okay, but really that is corresponds to a field inside. And of course, this excess charge is the mobile electron C having shift here. It's an excess of electrons, and here we have a deficiency of electrons, so the positive atomic cores are peeking through a little bit. So it's a complicated process, but in the end, it polarizes in such a way that the net field goes to 0. Yes?
Why does it charge build up on all those corners?
Why does the charge build up on the corners? I don't have a really good qualitative way of explaining that.
Is it something with the surface area being able to get farther distance? Maybe they can spread their charge faster on a corner than they could in some place?
It's not a dynamic thing, so it's not a matter of faster, but it works out. That in fact you get a lot of charge on points, on pointy things. So lightning rods are pointy, so that when they polarize, you get a lot of charge there, and charges in the lightning are attracted. And I don't have a good I think it's a little bit counterintuitive, frankly. I think that piling up charge in the corners means they're all close to each other, so why would it do that? But it always, in every program I've ever written, and in every book I've ever read, and in every measurement anyone's ever made, it actually comes out that way. So if you think of a good qualitative explanation, I'd be pleased to hear it. All right, well, yes?
Because, like, the net field inside has to be 0, and that's just the way the geometry works out for it to do that. It has to wind up.
So the question is it because the net field inside has to be 0? And the geometry works out. Yes, that is how the geometry works out. But it's always a little surprising that it does work out that way, because you'd think that, yes, it works out great that the field in here is 0, but we sure have a lot of electrons crowded together in a small place there, but it turns out that repulsion is balanced by the repulsion due to all the other electrons in other places. So it works out. It does work out that way.